Can you see me
Yes, sir.
and my slide?
Yes, sir.
Okay, thank you. Good morning, everyone. Have a good day. My name is Shaharia Chaudhuri. I'm lecturer at Friends of Songkhla University. My research interest are solar energy, renewable energy, solar waste recycling, e-waste. Today, I'm going to discuss about solar photovoltaic module recycling. We know the we know about the solar energy, most promoting energy currently, and there are many advantages of solar energy. So if we may not recycling, and we know that solar energy lifetime only 25 years. So what happen in future if we not recycling the solar panel? So this is the scenario of solar photovoltaic cumulative data. We can see that in 2009, it was only 23 gigawatt installed globally. And 2010 and 2011 is rapidly increasing. 2011, it was 70 gigawatt. And we can see also that 2012, it crossed 100.5 gigawatt. It's rapidly increasing. And we can see surprisingly, in 2015, it was 230, almost 30 gigawatt installed. Surprisingly, 2016, it was little bit fall down. And if we compare 2009 to 2017, it's a huge difference. And between 2016 and 2017, it's like almost double installed globally. It's like 400 gigawatt. Can you imagine that what happens after the 20 years? In by end of 2017, here's the some data of different countries and also the market share. We can see that Spain, they install 1% of a global from global data. We can see that Spain installed 1%, and United Kingdom, UK, India, Italy, Australia, there is not big changes like 2 to 3% difference. But if we look to the Germany, compare with Germany, it's almost double, 11% installed. And Japan, Germany, Japan, and USA, there is no different big changes, but 1%, almost 1 to 2% changes. And rest of the world, only 14%. And we can see also, surprisingly, you can see China, they dominating still now they are dominating the global market. We can see that China installed 32% total of installed in global over the world. Can you imagine that? And we can see that the difference between China and others country, and our developing country still not is focusing, right? But it's almost growing up. So before go to the recycling part, I want to show you one video, and you may get some idea about the solar photovoltaic energy and the materials, everything. So let's enjoy the video. This episode of Real Engineering is brought to you by Brilliant, the problem-solving website that teaches you to think like an engineer. Install
Installed global capacity of solar cells has increased year on year for the past decade.
Video sound is okay?
Yes, sir.
Yes,
We can hear it
yes,
clearly.
Plummeting prices and rising
At this time, there is no sound, sir.
No sound?
Yes, sir. No sound.
Okay. Okay, wait. Stop sharing.
This episode of Real Engineering is brought to you by Brilliant, the problem-solving website that teaches you to think like an engineer. Installed global capacity of solar cells has increased year on year for the past decade, fueled by the plummeting prices and rising efficiency of solar cells, forcing fossil fuel producers out of the market through technological advance. At the end of 2019, the total installed capacity of photovoltaic cells exceeded 630,000 megawatts, an astounding figure that is going to continue to rise in the coming decades. However, in the 40 years we've been using solar cells, there has been a mystery flaw that has been sapping away potential electricity from the photovoltaic cells. Upon testing in the laboratory, newly manufactured solar cells display an efficiency of about 20%, meaning they can convert 20% of the incoming energy from sunlight into electric current. However, within hours of operation, that efficiency would drop to 18%, a 10% drop in total electric generation. Losing 10% of 630,000 megawatts of power is no small problem. That's equivalent to about 30 nuclear power plants worth of power capacity if the solar panels could operate all day, which they can't. But you get the point. There's a lot of potential electricity being lost. It's no wonder that scientists and engineers have been hunting down the cause of this problem, termed light-induced degradation, for 40 years. And last year, we may have finally cracked the problem and found the cause behind this mysterious loss in power. To understand it, we first have to understand how photovoltaic cells work. Photovoltaic cells use the photovoltaic effect to generate a current, an effect where photons of a particular threshold frequency striking a material can cause electrons to gain enough energy to free them from their atomic orbits and move freely in the material. This is best achieved with semiconductors, whose unique properties lying between conductors and insulators allows them to most easily elevate electrons from atomic orbit to moving freely among their atoms. Some of the first solar cells were created with selenium, like this one, created by Charles Fritts sitting atop a New York roof in 1884. A revolutionary device that produced a consistent current of electricity, but it was achieving an efficiency of just 1%, converting 1% of the energy striking it in the form of light into electricity. This, in combination with the high cost of selenium, made it an unviable source of electricity. To succeed, these devices needed to compete with fossil fuel power sources. Before the photovoltaic effect could power the world, scientists and engineers would need to figure out how to increase that efficiency percentage and to do it with cheaper materials. Enter silicon. a common semiconductor material that has formed the bedrock of the electronic age. This is going to be our starting material for our solar cell. Let's build a solar cell from scratch and see how efficiencies were gradually increased over time. Let's first look at what happens when light interacts with a pure silicon crystal like this. Incoming light can do one of three things. It can be reflected, absorbed, or simply pass right through it. If light is reflected or passes through, it cannot produce the photovoltaic effect. Step 1 to improving our efficiency is to minimize the amount of light that gets reflected off the material. This is wasted energy that affects our efficiency level. In fact, 30% of light that strikes untreated silicon is reflected. So, before we even start, our maximum efficiency drops to 70%. For this reason, silicon is often treated with a layer of silicon monoxide which can reduce the light reflected to just 10%, while a second layer with a secondary material like titanium dioxide can reduce it as low as 3%. Texturing the surface of the material can further increase the probability of light being absorbed. If it is textured like this, light that is initially reflected has another chance to strike the material and be absorbed. Only light that is absorbed can potentially cause the photovoltaic effect, but not all light will. We need photons above a threshold energy to increase an electron's energy enough to allow it to move freely in the material. A photon's energy is defined by multiplying Planck's constant by its frequency. Silicon requires photons with 1.1 electron volts to produce the photovoltaic effect, which corresponds to a wavelength of 1110 nanometers. This lies around here in the light spectrum, and any lower energy from here down cannot produce the photovoltaic effect. This light will simply cause the atom to vibrate and create heat. This graph shows the total solar energy being emitted by the sun. However, a good deal of this does not reach the Earth's surface as it is absorbed by the atmosphere. This is a more realistic graph. About 4% of the energy reaching Earth's surface is in ultraviolet, as the sun emits relatively little ultraviolet photons. 44% is in the visible spectrum, and 52% is in the infrared spectrum. This may sound surprising, as infrared is lower energy, but it covers a wider range of the spectrum and thus accounts for more energy. Because silicon cannot make use of light with a wavelength greater than 1110 nanometers, everything from here up is energy we cannot convert into electricity. This represents about 19% of the total energy reaching Earth. Another thing to note is that light with higher energy does not release more electrons. It simply produces higher energy electrons. Blue light has roughly twice the energy of red light, but the electrons that blue light releases simply lose their extra energy in the form of heat, producing no extra electricity. This energy loss results in about 33% of sunlight's energy being lost. So, these spectrum losses alone cause a 52% loss in efficiency. This is a lot of energy to lose, but silicon sits near the ideal threshold frequency that balances these two energy losses, capturing enough of the lower energy wavelengths while not losing too much efficiency as the result of the material heating up. This is such a large loss in power that in some climates, active cooling, which takes some of the electricity the panels create to cool the panels, actually results in more electricity being generated. The reason solar panels lose efficiency as they get hotter is quite complicated and outside the scope of this video, but for now, all you need to know is that silicon balances these factors best for terrestrial purposes. Onto the next problem. Knocking an electron free by itself does not create an electrical current in our circuit. It just frees an electron to move freely about the material. To create a useful current, we have to force this electron around an external circuit where it can do work. Freeing an electron also creates a positively charged hole in its place that is also free to move about the material. If an electron meets a hole, it simply fills it and our energy is wasted. The next trick to maximize efficiency is to limit the chances electrons have to fill these holes and to force them into our circuit as quickly as possible. To do this, we use the unique properties of silicon. Silicon has 4 electrons in its outer shell, and thus readily forms a crystal structure with 4 neighboring atoms using covalent bonds, a bond where neighboring atoms share an electron pair. We can manipulate this behavior and tailor the crystal's material properties by adding impurities called dopants. Say we add boron atoms to the silicon crystal wafer. These boron atoms have 3 electrons available for bonding with the silicon crystal, but silicon wants 4, so this creates a hole in the crystal that wants to be filled with an electron. We call this a p-type, as it has positive charge carriers. Now, let's say we create another wafer of silicon, but this time we add atoms with 5 electrons available for bonding, like phosphorus. Again, the phosphorus bonds with the silicon, but this time we have an extra electron that can float freely about the material. We call this an n-type because it has negative charge carriers. Now, let's sandwich these 2 materials together and see what happens. The positive holes and negative electrons migrate towards each other. The electrons will jump into the p-type and the holes jump into the n-type. This causes an imbalance of charge because now the p-type has more negative charges and the n-type has more positive charges. We have just formed an electromagnetic valve that allows electrons to pass in one direction. Let's see how this works. Suppose a photon with sufficient energy enters the p-type side of the solar cell and knocks an electron free. The electron starts bouncing around the material and one of 2 things can happen. It can recombine with the hole, resulting in no current, or it can come into the electromagnetic field at the junction of the materials. Here, the electromagnetic field actually accelerates the electron across the junction into the n-type side, where there are very few holes for it to fill, and to boot, the junction's electromagnetic field actually prevents the electron from passing back to the other side. A similar thing happens on the n-type side, where holes are selectively transported across the junction before they can recombine. This means one side of the junction becomes negatively charged, while the other side becomes positively charged. We have created a potential difference, or in other words, a voltage. If we add some metal contacts and an external load circuit, these electrons will pass along the circuit to recombine with the holes on the other side. We have just created a solar cell. You may notice a problem here though. By adding metal contacts to the upper surface of the solar cell, we've just blocked light from entering the cell and thus reduced its efficiency. This is yet another problem engineers have had to think carefully about in their quest to optimize solar cell efficiency. Over the years, engineers have optimized both the shape and manufacturing techniques to minimize the area covered by the metal electrodes, while also minimizing the resistance the electrons will face in entering the external circuit. One research paper used topology optimization to design these electric contacts. Topology optimization uses algorithms to optimize the design of objects using constraints the engineer inputs. Using this method for the electric contacts produce something remarkably like the vasculature of a leaf. That shouldn't really surprise you. Vasculature on a leaf does not perform photosynthesis. It instead brings the water that is essential for photosynthesis to the leaf and extracts the useful products, serving a similar purpose as our electric currents. So, of course, plants have developed the perfect shape to optimize the energy they can absorb from the sun. Plants have had millions of years to evolve this shape. However, most solar cells use a simple grid shape, as it is cheaper to manufacture. This typically results in an efficiency loss of about 8%. All told, these effects result in a typical modern solar cell having a laboratory-tested efficiency of 20%. So, what was happening to cause that drop to 18% after a couple of hours of operation? This problem was the focus of hundreds of scientific papers, and many found clues to the problem. Many noted that the efficiency drop was correlated to the concentration of boron and oxygen in the silicon, and noted that the drop did not occur when boron was substituted with gallium. Thus, it was known a boron-oxygen defect was causing the issue. Others found that the defects could be reversed by heating the silicon in the dark at 200 degrees for 30 minutes, but it would return once again upon exposure to the light. Efforts in reducing the problem have primarily focused on reducing the concentration of oxygen impurities in the silicon wafers, which occur as a result of the silicon manufacturing technique that is the source of 95% of silicon solar cells. These manufacturing techniques are still a point of research, and the engineers and scientists were working blindly. Little was known about the actual defect creation process and how exactly it was causing such a large drop in efficiencies, leaving engineers with less information to solve the problem with. This paper used a special imaging technique and observed these boron-oxygen molecules converting into something the paper refers to as shallow acceptors when exposed to light. In essence, they observed the defects transforming into little electron traps that acted as recombination sites, and thus reduced the time and probability of electrons entering the circuit to do work. With this knowledge, engineers can now develop better techniques for preventing this phenomenon and hopefully increase our renewable energy capacity in the coming years. It's easy to think that technology has reached a point of being so advanced that knowing where things can be improved is practically impossible for the average person, but that simply isn't true. A little bit of research into any area will reveal countless problems humans are still grappling with fixing. When I started researching this video, I knew little about solar panels beyond the basics. In order to make this video, I took a week to deep dive into some college textbooks using my knowledge of material science and electronics to guide my research. But I had some gaps in understanding that the college textbooks just assumed I had pre-existing. This episode
Hello. Yeah, this is the structure of material and manufacture of solar cell, the story of solar energy. So how can we manage the solar waste? So reduce, reuse, and recycle. That can help us to protect our environment for as a research and development and technology advance continue with a maturing industry, and the composition of a panel is expected to require lost raw materials. And secondly, rapid global growth is expected to generate ro- uh, robust secondary market for panel component and materials. And third, as the current photovoltaic installations reach the final decomposing stage, and recycling material recovery will preferable to a panel disposal. This is the scenario of solar photovoltaic waste. And if we not think about now, so what happened in future? And researcher predicted that this is the scenario if we in by end of 2016, and the waste become a 43,500 ton. And we can see that, and also it's reported that by end of 2050 it would become a 78 million ton. Those is if we compare the it would be 4,500 gigawatt solar panel produce 78 million ton. Can you imagine that what happened in future? How can we manage it? Because of we know that the solar panel lifetime only 20 to 25 years. So this is the scenario behind the scenario of solar energy. So we need to think about that, because if we may not think if we not think about that, how could we recycle it, or is it possible to recycle and or not, so it destroy our environment. And also due to the resources, we cannot save our resource also. Solar panel recycling process, there are many processes. So we can see that this is a module in Belgium. We can see that solar panel has a different kind of materials like lead, copper, gallium, cadmium, aluminum frame, silicon, and synthetic material, many materials with a solar module. So that kind of things, if we not recycle, so that can for example, lead is very hazardous material, we know that, heavy metal, and cadmium also. So if we not recycle it, destroy our environment, and like water pollution. Yeah, so there are the various materials need to be separated properly for recycle. And also the undamaged solar cell that can lose the efficiency due to the recovery or reuse, so need to be proper alignment and need to be recycled in future. The main technology of so main type of solar technology, we know that currently available silicon based solar cell. So we can see that solar panel technology is a composition is important and considered when recycled. And silicon based solar cell, there are two types of crystalline silicon and polycrystal, monocrystal and polycrystal silicon. So multi silicon panel have a 50% market share, and monocrystal silicon panel 45 market share. So, and also there are others solar panel like thin film based solar panel, CIGS, CDTE. They also have available in the market, but in future we need to recycle it. And this is the market share. Last time I showed you that market share 2014, it was 92 for silicon based first generation solar cell, and 7% for second generation solar cell, and third generation solar cell 1%. It was 2015 14. And by researchers predict that, and according to the IEA arena, International Renewable Energy Authority reported that by end of 2030 it would become a 44.80% silicon based solar module market share, and 44.10% it would be the third generation like perovskite solar cell or disensorized solar cell. It would become market share 44.10%. And others like a second generation solar cell, due to the efficiency issue, it would become 11.10%. This is the waste generation scenario. How can we predict that when it would become a waste? We can see that in 1985, those panel installed 1985, it would become a waste 2012, almost 2012. So how can we calculate it? This is the mathematical calculation. We can see that the year of installation is X, and the year of waste generation Y. So Y is equal to X plus 25. So researchers predicted this 25 is actually lifetime. We can make it 20 also, because some solar panel lifetime 20 to 25. So if we think that 20, then we can calculate it when it for example, if 2000 it installed 2000, then it would become a waste 2020. So this is the year of waste generation scenario. Potential value creation through photovoltaic end of life management. This is the cumulative data 2020, 30, and 2050. We can see that end of management photovoltaic panel with span new industries can support, consider the economy value creation, and it consistent with the global shift of sustainable development. and estimated would rise to 8 million ton by 2030, and a total 78 million by 2050. And we know that there is some report. Uh, there is some report. Uh, 2.6 megawatt solar panel. So 2.6 megawatt solar panel installed. When it became a waste, and it reduced 1,480 ton CO2 emission in their whole life. And so that is the big thing. Actually, that is the big thing, and we can see that the scenario, that is the big thing. And if we not recycle the huge dangerous big obstacle for us in future industry. But we can think about that. So there is a many reason for broken the solar panel. Is like a lifetime, not only lifetime, there are many losses, like we can see that unknown defect and transportation damage, frame loss, manufacturer loss, and some solar panel lost the efficiency due to the manufacturing, and optical failure. There are many not only lifetime, there are many reasons solar panel can become a waste. So, and also the weather condition, because sometimes windy weather or natural disaster, that can also destroy our solar panel. So solar panel, is it possible to recycle? What do you think? So we can see one documentary. Hello, am I audible?
Yes, sir. We are still here.
So what do you think about solar photovoltaic now? Do you have any idea?
Uh,
Do you
maybe,
think
sir.
for that one?
Yes. I think, sir, if you're going to, in my own perspective, sir, if you're going to create more solar panel in our community, for example, so what will happen if in the future, because it is mentioned in your presentation that by by year 2050, we can possibly accommodate up to 78 million tons, metric tons of waste coming from Phoebe. So do you think this is advisable as a renewable energy in a particular community or in a country as a whole, since some of the components or the elements are very hazardous materials like the cadmium and the lead. Thank you.
Okay. Okay. Yeah. Actually, it's possible for it's possible to recycling because before actually problem is that we never thought that they have the behind the scenario is different, and even we think about other renewable energy like marine energy, they have also some negative impact, but we may consider it, and we may consider it, and we can we may consider it, and it's possible to reproduce the solar panel, and it also we can save also our environment, just to take initiative. Recycling process after end of life, or when solar panel become a waste, so we can do the physical separation, then thermal treatment for remove the EVA layer, and chemical treatment it can separate. We can see that physical separation, we can separate glass, aluminum, other component, and also that we can recover the silicon. We can recover the solar cell, and then thin film. If thin film, there is a different treatment, and also if silicon, there is a different treatment, and we can throw it to produce a new we can purify it and reuse it to produce a new panel. So it's possible actually. Yeah, first we can see that as a silicon based solar cell. Yeah, the silicon based solar cell. So how this is the waste volume. How can we calculate the amount of solar in the like annual capacity divided by power, and divided by module, and into the weight, and divided by module is equal to weight PUM. So silicon solar photovoltaic recycling process in there are many researchers, they provide a different kind of method for recycling. Some recycling process available, and still now it's under research actually, because of the company manufacturer, they just concerned about the installed solar panel maximum. But some of company like Solar World, First Solar, they have own recycling plan, but due to the some of them, they want to say that it's not still now we don't have too much materials or something like that. But this is not issue, but we can recycle our materials, and we can see that the major component of the silicon, crystal silicon panel, and including glass, aluminum, copper, can recover at cumulative yield and greater than 85% by panel mass through to the purely mechanical separation. If we do the mechanical separation, then 85% can recover, and separation of the major components such as laminated glass, metal frame, wiring, cable, and polymers. First step in current and first generation solar process, and the aluminum or steel frame, we can reuse it also, because when it become a waste, we can reuse it like a cable. We can reuse it. It's not effect too much, so we can reuse it, and this is the process of we can see that Komodo, they provide this method, like how we can recycle the solar module, and this is the recycling process for CIGS, thin film, silicon based solar cell, or CDTE. We can do that. This is a Solar World. They have the recycling module, and source of secondary silicon, like silicon. When we recycle, what happens? How can we collect it? We can see the wafer, cell process, when we separate the mechanically separate, and also the module assembly, like this one. And after recycle, we melt it, and this is the crystallization. And other applicant we can use, and semiconductor industry we can use it. Second, silicon we can use as not only solar panel, we can use the semiconductor industry. And rest of the we can purify it, and we can reuse it. How can solar panel recycling ingot parts, what they did, like a surface cleaning, first surface cleaning and etching by chemical, and surface, they can prepare it for reuse. And how they did, this is the solar world recycling process. And recycling wafer and cell scrap, broken wafer, and wafer with emitted and air coating, they remove it, and they use the hydrochloric acid and other chemical for etching and purify it. And this is the silicon, pure silicon powder. So they throw it for new solar, produce a new solar module. So recycling technology, there are, we know that a thermal process, a mechanical process, chemical process, and this is the mechanical separation, limited glass recycling. We can see that high capacity available, and if we separate, we use that method, and universal process, and also impure function. And we can see also the thermal separation for just EVA layer. For normally thermal separation used for remove the EVA layer, and we can see that very universal process and cost effective. And material, we can use the material separation, waste gas cleaning, dust remove, and chemical, that's one chemical process, only focus on the thin film module, and cost of waste treatment of chemical, and strong dependency on material used. And we can see also this one also. So this is the three waste treatment technology. We can see what happens when after recycling, and this is the way. So now I would like to show you one recycling process, how they recycle, one documentary. This is the ongoing recycling process for solar world. They are following this strategy. They use like a thermal process, manual separation. First, they do the manual separation, and first like a module assembly, and then new module. This is the actually new module, and after end of that, they process thermal treatment for remove the EVA layer, then manual process to separate other component like aluminum and other, and then they use the chemical for etching like see, we can see here also, and this is the reprocess of produce a new solar cell. We can see that how they did it. After recycling, they provided some information about that what kind of the recycling they did in this is the in Germany, double glass module and stainless steel frame, and it was a monocrystal silicon, and this is the panel structure, and the number of cell module 20, so dimension is that. And this solar panel, they collect a solar panel from Belgium. It was installed in 1983. It was 1983, and it's old solar module, like double glass module how it look like, and double glass module, stainless steel frame, and cell type 4-inch monocrystal, and the back seat metallization silver. They use conduct as a conductor. They use silver EVA polymer lamination, and this is the structure, and 36 per module, 36 cell. So they can recovery. They show after recycling, they show that 96.96% glass they can recovery, and plastic there is no data, and broken cell, like if broken cell, it they can recover, they could recovery 84.62%, and copper, aluminum, and junction box, they don't have data. So totally actually they provide the data like totally it possible to recovery 84.57 and more than that. So it was 2009, almost 1900 module. And also the current situation and rate of wholesale, and they show that the predominantly damaged product, and reduce valuable material, wide parity of module type, reduce the cell thickness. So this is actually rate of we can see that rate of wholesale. The requirement for new treatment and recycling of PV module. And this is the automated process. They don't need anything, or whole process by automatically, and we can see the reason for need a new produce, requirement for new treatment. This is the how they did actually. We can see that use a new sort of solar photovoltaic install, then it broken after the end of life, and they use thermal treatment like 600 degrees centigrade in the oven. They separate it, and later on use sorting and clashing after thermal treatment, separation of component, like they broke it, melt it, and after melting use the chemical treatment, use chemical, and after chemical treatment make a crystallization of silicon. So they showed it's like that. and it can throw for produce a new solar photovoltaic module. This is also the current scenario, situation and rate of solar photovoltaic, like first generation solar current process, manual feeding, thermal and manual strong, and how they did it. And we can see the how it help actually global warming potential. We can see that silicon solar grade is like 100, almost 100% we can recovery, and other side wafer break and side, and we can see that it greenhouse gas related or recycling process is like CO2 equivalent. And we can see this one also, environmental module recycling. If we do the recycle, what happens in future? uh, this is the ecological assessment or life cycle assessment. After the recycling, the recycling of module was evaluated concerning its environmental effects by an life cycle assessment for all impact categories. This burden due to the reuse of silicon material and glass is higher than the burden of environment. So if we recycle it, so we can reuse it, and they show the recovery rate. Uh, just silicon recycling 75%, and waste other waste it would be 10 to 20%. This is the economical value we can see from here. This is the economical value of solar panel. After solar panel recycling, we can see that how can it help to produce a new panel, and we can save also, like our new, if we recycle and reuse the solar panel, so it can reduce the cost also. And also we can see the economical value, like 90% we can recover. Earlier I showed that, mention it, like internet, and it can possible also. We need international collaboration, and we need to company need to make a policy. There are many things. Okay, let's start about second generation solar cell, CDD, thin film solar cell, because we know that thin film based solar cell is actually fabricated by hazardous material like CDT, cadmium telluride, or CIGS. This is the process of fast solar. They following this strategy for solar cell recycling, because Fast Solar is the only one company who those produce only the CDDE based solar module. They manufacture only that one, and their recycling process, like a panel recycling process, Fast Solar solar panel, and they use this strategy. And we can see that the prominent example of this process include the following step. There are some they follow also the some researcher, they showed their opinion, and it can possible to recovery 90% glass and about 95% of semiconductor materials. And we can see panel are shaded and crushed in hammer mill. When the mechanical separation, they use the hammer mill to mill the solar solar semiconductor materials, and about 5 millimeter. The size is 5 millimeter to break the lamination bond. When they break from EVA layer, separate from EVA layer, and the dust is then collected, and aspiration system equipped with a high efficiency particulate air filter. Semiconductor layer etching is carried out with a mixture of sulfuric acid. They use for chemical treatment sulfuric acid, hydrogen peroxide, mixing together for purification, and the glass larger pieces of ethyl EVA layer, ethyl vinyl acetate are separated in classifier and vibration screen. Finally, the glass is rinsed with water and dried on a Bell filter unit. The final step, the filtration liquid with the metal can be extracted via the exchanger or participated. The cadmium and telluride. There is a two kind of materials can be further purified by the third phases of the reuse of the solar industry. So this is the uh, process of solar panel. Um, First Solar, this is their recycling plant. They did a different. They have a recycling plan in Malaysia, and also they have in Europe. They have some recycling plan to recycle the thin film based solar cell like CDT, their own solar module. And we can see that established first global and comprehensive module recycling program in the PV industry in 2005. And only PV company offering globally available high value recycling. And recycling facility are operational in all manufacturing plant. Scalable accommodated future high voltage 48,000 metric ton recycled to date, and continuously improving process and technology, reducing the operational cost. So primarily they are now doing recycling process, but they try to improve the technology for reducing the cost. And we can see that the Fast Solar product development striving for continued improvement of our technology and ensuring that they ensure ensuring the recyclability full integrated module. They are trying to develop their recycle friendly design, and they try to develop a budget for recycling plan. And they also follow the CMS, change management system. This is their strategy. So Fast Solar recycling process, this is the module recycling process, how they recycle. And we can see that this is the recycling process, how they have own recycling plan. Size detection, filtering, how they did a third-party refining process, semiconductor CDTE. For CDTE, we can see that main leach copper treatment, tellurium reduction, cadmium participation, and they how they separate CDTE. The product recovery and quality, they ensure that 90% module weight recovered, and most of this glass can full glass can recover, and glass will be reused for new glass production. And it can help to produce a new glass production. And also the cadmium recovery 95%. And also that can make a partnership with third party for producing a new solar module. So they have three recycling like period 1, period 2 in 2006. They did based on the minimum industry beach process. They did and volume output ton per day, 10 ton per day, and capital investment $5 million. And in 2011 they increased their volume output like 30 ton per day, and investment $7 million. So this is the Fast Solar recycling process. We can see the video. Okay, na? So this is the second version of First Solar module recycling, First Solar company. Now how they did hammer mill and how they separate. They improve their strategy when they recycle the second version, and how they separate each materials, and they can recover 95% materials, semiconductor materials, and 90% of glass. And third generation continuous process, like more efficient, 24 days, 24 hours, 7 days, and 30 ton per day capacity, and high quality, and also they ensure the targeting the cost below hazardous waste disposal by 2015. They had target, to reduce the cost of hazardous material disposal and recycling facilities. They are committed that they try to establish the recycling project each country. For example, they have the, for Asian region, they have a Malaysia, they has a um, plan for module fabrication. So at the same time, they will collect their module from the field level after when it become a waste, and they take it back and recycle it. And they thought that per day they can recycle at least 350 ton. So this is the recycling benefit, and they showed their 4 volume, how they recycle, and they by 2027, the cost, process cost, how per ton kilowatt, and life cycle benefit of CDT PV module. We can see that transport to 20 ton per truck. How can they transport it, and how can they what kind of materials or chemical they use for recycling, like sulfuric acid, and they need electricity. This is actually per metric ton, meter per meter square module. Like they use a deionized water, hydrogen peroxide, sodium hydroxide, CDE emission 2 year, CDE emission 2 water disposal. So impact benefit, environmental credit. They also focus on environment and life cycle assessment. They did all kind of things, material assessment. So the socio-economical and environmental benefit for high value of recycling, like use of environmental sensitive materials like hazardous materials, CDTE, lead. It can recycle, and it can reuse for second PV fabrication. And also the others materials also can reuse for industrial section. And we can see that if we do that, we can they expected 16.5 billion euro by end of 2050. The huge industry in future generation. And ensuring the supply raw materials, the maximum resource recovery, 10 to 50% CDE if we produce. And also they are committed in future they will produce a new solar module from recycled materials, 10 to 50%. They reuse it, because when they recycle, they ensure the quality, and they reuse it for producing a new solar panel. And also the improve the material efficiency, ensuring after recycle we have to ensure also that after recycle it can be reused, because there is no benefit if recycle and material cannot after reuse it's not efficient, the module efficiency is not good, so will not good, so that is the thing. So now third generation solar cell, actually we know that third generation solar cell still now under research. That is my own work I did last 2019 in Malaysia. Is it possible to recycle? Because of for sustainable development, we need to think before launch any product. After it become a waste, what can how can we reuse it? Because of otherwise we will use many hazardous materials. Is it possible to recycle? So my work was fabricate a new solar cell and ensure ensure the unique method for recycling. So this is the layer by layer separation process. First, we fabricate the solar planar structure solar module, and then we the solar perovskite solar cell, and then we recycle, use a four-step method like layer by layer separation. First, chlorovenzene solution used for 3 minutes, and remove the gold layer, because as a electrode we use a gold and spirometers for STM layer. So we remove it by using the chlorovenzene solution, and after that use DUI water for reduce the methyl ammonium iodide, remove the methyl ammonium iodide, and after that use a DMF solution for two minutes, remove the lead iodide. Last but not least, DMF solution use 10 minutes for remove the TiO2 layer, and we successfully recover the FTO substrate. Because of perovskite solar cell we use FTO substrate, so we can remove also FTO. We tried the time that we can reuse the FTO after recycling, recovery all materials. We just glass and FTO substrate, we keep it and we can reuse it. Is it possible? So in the lab, this is our separation. uh, we use different four kind of method, and this is the gold and DMF solution. This is the FTO, and we separate it. And also we use one step solution, two method. I apply two method, one step solution and step layer by layer solution. So one step method, we just use aquaresia solution for 10 minutes, and it can help to recovery the ITO substrate without any effect, a little bit, but it's not big effect. And separate the others chemical component, like one solution, spiro and lead, methyl ammonium iodide, TiO2, all in one solution, and separate it, and we recovered successfully recovered the ITO substrate, and for fabricate a new solar cell. This is my working time, and when I fabricated the perovskite solar cell, and then uh, I got 7%, 6.215% efficiency, and due to the stability issue, it degraded. So how can we ensure the quality of recycling, like in future when it would become available, it will become available in the market? So how can people trust us? So there are many explanation. For example, we use FECM. This is the SCM result. After this is full cell, after fabricate the full cell fabrication, like this is a gold layer, spirometered layer, and this is the perovskite layer. Perovskite layer means the methyl ammonium iodide and methyl ammonium lead iodide, and this is the TiO2 layer, and the thickness is very perovskite layer thickness was 300 nanometer, Spiro 80 nanometer, gold 40 nanometer, and TiO2 80 nanometer. And FTO we collect from commercial FTO from Sigma, and the FTO thickness was 500 nanometer. So this is the difference between we compare with recycle after recycling and fresh FTO. This is the fresh FTO, and this is the recycled FTO, and we compare it, and there is no changes after recycle. This is a one-step method result. There is no changes after recycle. So we can ensure that the thickness of FTO after recycle, there is no changes, so we can reuse it. Not only that, we use another another analysis like DMF solution. We use UV, and we detect the hazardous material. For example, we use by UV UVVs. We analyze this, and we detect the lead presence. We can see the lead because we use DMF. If we use a DMF, there is no signal, but we got the lead. This is the references we use. We dissolve fresh lead with DMF solution, and also we check our separated solution. So there we can see that the signal for after 400 to 500 is same. So we can ensure that lead presence. And also the spirometer we use with a chlorobenzene solution, and we compare it. It's similar. So quality of a spiro, when we did we did the process chemical solution treatment at that time, is there any effect on chemical bonding? So we can see that this is the NMR after recycle, and we can see that this is a benzene structure, and aromatic group. We know that benzene aromatic group spirometer, so we can ensure the quality of also the spiro. So after the second, we see that and we use another method detector like ICP-MS. ICP measurement result and show that the DI water into the DI water 17.42% per milliliter, and DMF solution 40.22. So according to the US, the concentration was low because we used just only one cell. So if we do many cells together, so that can help. We can find more lead, and it possible to recycle. And according to the US environmental protection, like that, if contain 5 microgram, then at least 5 microgram is a hazardous. It would become a hazardous according to the US Environmental Protection Agency, EPA. So titanium, we also find out the titanium because the titanium was very little amount. We check FTO analysis by structure quality by XRD, and we compare with reference FTO and recycle FTO. So we got same peak. So there is no big changes. So we can ensure that the quality of XRD also FTO also there is no changes. So we can it can also prove that we can reuse it. And we check the EDX analysis, and we check the percentage of element FTO. This is the reference FTO. This is the recycled FTO. So we can see that tin oxide, because fluorine is gas, it's not visible. FTO means fluorine doped tin oxide. So we just see the tin carbon, silicon. So we can see the percentage of tin 72.9%, and recycle 70.8%. There's not big changes actually. So we can that can also ensure the quality of FTO. And earlier we mentioned that if transmittance and absorbance is not good, so we cannot get good quality. We cannot get efficient electricity from solar module. So because we know that we use FTO for transmittance, so we check the transmittance of FTO by using UVVs, and there is no big changes. Recycle and also the fresh FTO. This is the electrical properties, and we ensure also the quality of electrical properties, like there is no big changes. So that can also the ensure the quality of FTO. And we check the roughness of recycle FTO and also the fresh FTO, and there is no big changes actually, just as 27.711 and 27.700. So there is no big changes. And we check the gold after recycle the gold, and we ensure the quality of gold. Is there any changes of gold, purity of gold? No, there is no big changes. There is no changes actually, not big changes. There is no changes. And we compare with the literature review, and that all can actually ensure. And this is the actually ITO based, it's a one-step process. So it has a little bit changes actually due to the time limitation. We haven't done after that, because COVID came and we cannot access in the lab. So that's why still it's pending, just only two results. In future, I believe that in future it can be developed industrial level. And this is the process of solar silicon based solar module recycling from literature review. And many researchers, they establish their own method, and we can see that physical separation, there is a advantage and disadvantage also, like efficient waste handling. Okay, before I discuss about that, are there any question regarding perovskite recycling? Hello, sir. So this is the silicon solar cell mode. This is the separation, physical separation. This is the advantage and disadvantage. There are many process for some thermal treatment. We can see that EVA layer, like nitric acid dissolution, complete remove EVA metal layer from the wafer, and dangerous for emission. And we can see the thermal, if we follow the thermal treatment, EVA fully eliminated. And this is the advantage, and disadvantages involves a high energy consumption. So material separation, dry and wet chemical process, non-chemical process. Advantage is a non-chemical process, no removal, dissolve solid, simple process. And etching process, we can see the same simple and effective process. So there are also many process for this is for a thin film, many recycling process. And there are also the positive effect and negative. This from according to the literature review, many researchers, they um, reported that their own experimental result. And still now some of research under some of result is under research. And this is the Thailand scenario. In Thailand, by end of 2010, it was 57 megawatt and installed, and by end of 27 it was 2640 megawatt. So capacity of estimated reach by 2036 it would be 6000 megawatt. And solar waste with up to 246 ton 46 ton having been dumped improperly local landfill first 2 decade. They haven't they didn't follow any recycling process. They just dispose on the field. And solar waste will rise to 80,000 tons by 2036 in line. So from rooftop installation, so they need in Thailand also need the proper recycling process. This is the scenario of Thailand, like how much they install, like northern part, northeast, central, southern part, Bangkok metropolitan region. There is some report, Bangkok News, they concern about a solar panel, recycling plant, PV panel, and recycling. They reported 2 times. They are also concerned about that. So Thailand recently, Thai government, they have some initiative for solar waste. They decided that they already took one initiative. Maybe they will very soon they will start recycling plan near future. This is the government policy for recycling solar module. And this is my one of my research actually highlighted in Singapore newspaper. 2 times they called interview and they ask about the future um, solar recycling. It's like Asian tracking solar time bomb. And without recycling loss, and the reason claim down hazardous waste by 2030. Another report, elephant in the room, can the solar industry go circular? So it was my opinion. In future, we can provide recycling plan design, and then that can help to recycle our module. One of my research article published, and after that it's highlighted many newspaper, 4 newspaper in USA, and blogs. They wrote, according to my article, they wrote blogs and tweet many things. This is my research article regarding recycling, and this is the recently published Perovskite solar cell recycling method in Royal Scientific of Chemical Society in RSC Advanced Journal. And I proved that the Perovskite solar cell can possible recycle with the environment friendly. And yeah, this is regarding the solar first generation solar cell. And that also the highlighted still now is top 3% downloaded, top 3 downloaded last 1 year, and highly cited, almost 70 cited. So that's it. Thank you so much. um, do you have any question or any opinion, sir? Can you hear me?
Yes, sir, we can hear you.
Yeah, Michael.
Yes, sir.
Yeah, do you have any opinion or any question, something like that? Or you know about that issue before? Do you have you had idea before, or just you just know today?
Well, most of what you present is new to me, so I'm still going over it in my head and processing it. But I don't have any questions of it right now.
Okay, okay. I think Mark Kelo, he has some idea about regarding this issue. Okay, Christiana.
Hi, sir. Thank you so much for your presentation. I knew about solar throughout like my research and studies and so forth, but I actually never thought about like the waste aspect of it. Like it's always thought of as like a good solution. I never thought about the waste aspect. And it's definitely something that I guess now that I'm definitely gonna look into. But I think one of the things that I keep thinking about is comparing it to like fossil fuels and like for example like decommissioning and so forth. It seems like it's still a good alternative, and I think that as we continue to use solar, there's going to be like a lot more research being done on the recycling aspect or making the products used in solar more like biodegradable and more like friendly to the environment. It's not really a question I have, just a comment on the overall. Like I never thought about the waste aspect of like a renewable source like solar.
Thank you, Christian. And Julie, Miss Julie.
Hi, sir.
Hello, Emma.
Yeah, I just want to give some comments
Yeah,
about
please.
actually the solar waste materials. Or yeah, are of course are not yet our problem here because we are not yet fully engaged. As I have mentioned, we only have yet 1.35% of our energy source is coming from the solar energy or solar power plant. So currently, of course, that should be our plan that we should take into consideration these solar waste. Um, but yet, I suppose we don't have yet that solar recovery facilities because as I have mentioned, we have just yet starting to engage in that source. Some example of source renewable source of energy. That's all.
Emma, yeah, this is the right time to know about a new field or new industry. This is the open a new era. Like you can think about now, and this is new for you and new for your country. So new idea you can think in future when you go somewhere, and you may ask them, and what is your recycling policy? Like when you talk, any company would like to, for example, Chinese company, they want to implement their plan in your country. So you are the policymaker, right? So you can propose them, what is your plan for after end the session? Will you take back, or we have to dispose in the field? So when you make a negotiation, like you have to confirm that if you sell your panel in our country, so before you have to committed that you will back it after when it become a waste. So it would not affect on like local people, because of we are general people, we don't know actually how to do that. So if for example, you see what is the problem currently now, everyone say that, oh, electrical car is environment friendly, right? What is the sources of electricity? We use burn coal and use electric car, right? So what is the benefit actually? We need to think about that. That is the big issue, in future. For example, you want to launch maybe new laptop. So before launch new laptop, you think about after end how can we recycle or how can we reuse it?
Yeah. Yes.
The big
Thank you for that.
sustainable development. This is the big thing of sustainable development. Anyone can give idea, but implementation or like circulation is a big thing now, because electrical, if we think that electrical car or electrical vehicle that can they have also battery, no one think about battery. Just say that, oh, electrical vehicle is environment friendly. It's not right. Like we without make a solution, we just involve we just invite a dinosaur, you know. We invite dinosaur as a we show them like as a friend, because if we don't think how to control them, so it would become a dinosaur, right? So
Yeah.
yeah. So what is the alternative? Like how can we replace electrical vehicle? Do you have any idea?
About the electric vehicle?
Yeah.
What do you mean by that?
It's like
Actually, yeah, I already get your idea. Yeah. Actually, I already get your idea about the some sort of contingency plan with regards to the waste, if in case we will be investing more on solar energy. Yeah, I get that idea. So yeah, I suppose we would be having already the policy if we are about to allow foreign investor investing on solar energy. Of course, we should be requiring them about how should they dispose this waste material. Yeah, yeah, I get that. So
do you know that just before yesterday, Sir Richard Branson, he went to space. Do you know that?
yeah, yeah, Richard Branson.
Yeah, Richard Branson. He dreamed maybe when he was uh, kid, right? That time he thought that he will go to space. Now it's very easy. So in future, actually, for electric, instead of when electric, we think about electric vehicle, so we can replace it by solar panel,
Yeah,
solar car, solar motorbike, right? Or solar
yeah,
power station for recharge, and or also at the same time, not only solar waste. At the same time, we make like other not only solar panel, electronic waste also. Same problem. Do you think about? Have you ever thought about your laptop or your television or your computer component? What happened when it become a waste? You just throw it. Do you know that how they recycle it? We don't know, right?
yeah. In the Philippines, some companies are they are already placing electronic waste bin in some malls. So if in case our laptops are already some sort not usable anymore, we are throwing them in some electronic waste bin that are usually placed in some malls in Manila. But in our case, in our city, the government itself, the local government unit itself, is also having this, waste segregation. So they are allotting electronic waste too for that. But I do not know if how does the city government implement. I do not know what happens to the waste, but generally the ordinary waste are going to our sanitary landfill. But the electronic waste, I don't know if they are already recycling that or they just returned it to the companies itself, the electronic companies that usually also recycle. I suppose Melissa has also an idea about that.
I'll come in later. Maybe
Yeah.
Melissa, she want to say something. Hello, sir. You are not audible. Still not audible.
Hello? Can
Yeah,
you
now.
hear me, sir?
Yeah, yes, sir.
Yeah, okay. Since since electronic wastes or we consider them as hazardous waste, the especially busted fluorescent, those contain lead and mercury as well. Also yung mga LED lights, we classify them all as hazardous waste. They don't go to the facility, to our sanitary landfill. So there are third-party collectors from our hazardous waste generators here in the Philippines. So they treat it in our in certain waste treatment facility. It's called a TSD or treatment TSD or TSF, where they treat all of those hazardous waste. So one concern is, like, for example, if solar panels will be introduced here in the Philippines, one issue will be, of course, manual separation, but then what about the extraction of lead, copper, all those hazardous components? So, like, in one example is that the removal of PCBs or polychlorinated biphenyls from our transformers. There are no treatment facilities here in the Philippines. We have to ship them to France. So similarly, I think we should mitigate or be able to set up facilities first, or waste treatment facilities for solar panels before we could introduce them into the Philippines. Or like what you mentioned earlier, we have to do partnerships. Like, if they will provide for us, they will buy back those solar panels, and they will be the one who will be treating, instead of us, the end users, who will be responsible for disposing the waste, which I think is another way on how we can introduce solar panels in the Philippines. So that would be for my input. Thank you.
Thank you. Harmony. Mr. Harmony one. Sorry if I mispronounce.
Yes, sir.
Yes, sir.
Yes. When I think about the entire process of the recycling of solar PV, I
Yeah.
think how about the levelized cost of electricity is include the recycling or only the manufacturing process? This is my question, because when I see the
Can you repeat it? Sir, can you repeat it? Repeat
yes,
your please repeat your question.
okay, sir. When I see the entire process of the recycling of solar PV, I think how about the levelized cost of electricity is include the recycling, because we seen the presentation from Irina that they say the cost of solar PV is decline over a time, but I don't see is it include recycling or no? How do you think about the LCOE? Thank you.
Okay. Your question is like after recycling, so it reduce efficiency, right?
Yes, that's right.
Okay. Yeah, that's why still now it under research. You are right. So we already know from a fast solar recycling process, they are committed that they will reuse the the material, semiconductor material, and ensure the quality of semiconductor, so that it would be same efficient. It would be same efficiency like as before. So they will make sure the quality. So if we do that, so it's like for example, it can be in future, it can be cheaper module. And also if we buy cheaper module, then we can reduce the electricity cost also, right? And then if we it would not affect our environment, so we can save it. Not only solar panel, and also if we think other thing, there is nothing free in the world, more or less, even renewable. If we think like wind power, they have also some radiation, but we can skip some of part, we can skip it. And do you think about wind power wind tower after in the stage, yeah, life, how can we recycle it? We need to recycle that one also. Yeah, your question is right, but it's still under research, but it's possible to produce same efficient solar panel.
Okay, thank you, sir.
Thank you, sir. Sir, I would like to go again 10-minute breaks, and after breaks we'll discuss about the policy. Policy means you just think some idea and you give me some idea. It's not like that. It's not like that it would be exact 100% correct. We just share our idea how can implement the solar panel recycling, because we need to make a good policy, company, stakeholder, and manufacturer, right? So we need to make a policy, and we need to propose our government, because you are all are from policymaker, from maybe ministry or some of our researchers. So we'll make a one policy, try to make a one policy, how can implement it, and that can we share not only for solar panel recycling, we can apply it other part also, like other recycling um, project also, like a plastic or electronic waste or other things. So after 10 minutes, we'll back again 11:20 and we'll discuss it and try to think about that. Thank you, sir. Have a good break.